All right. Hello, everyone. Welcome to another ACE Spotlight event. My name is Alireza Darbehani. I'm a machine learning engineer at the company called WSP. Sorry, I had an ad pop up. Before I get into the introduction of our great speakers today, I would like to make one announcement. We have a really great workshop coming up called Hands-on AI Products Workshop, going from concept to MVP in 5 weeks. I'm honored to host two great senior data scientists from the Nvidia team in Canada. They're part of the Canadian team that helps customers and partners use GPUs to tackle complex scientific workloads. So without further ado, Griffin and Mukundhan, floor is yours. Please take us away.
Thank you so much, Ali, for both the introduction and helping organize this session today. So hello, everyone, and welcome for those who are joining live and those who are watching the recorded session later. My name is Griffin, and I'm a data scientist at Nvidia, as Ali mentioned, and with me today is also Mukundhan, another data scientist with Nvidia. So both of us are a part of a large team of both data scientists and solutions architects at Nvidia that have a central focus on helping assist customers with their large, complex scientific workloads. Those especially that use GPUs and are using parallel computing today. So the format of the presentation today will be that I'll be talking through a series of slides for which the topic is going to be data science on GPUs and giving a bit of a gentle introduction to how you as a practitioner that is curious about using GPUs and wants to accelerate their work can use these ideas to go faster. And then as I talk through the ideas, Mukundhan will be monitoring the chat window, and so if there's any questions that pop up as we go, feel free to ask, and we'll either address them sort of on the spot through Mukundhan, who's watching those questions, or we will address them at the end of the presentation over video. So without further ado, but before we jump into the meat of the presentation, I wanted to give a quick introduction to Nvidia. I'm sure a lot of those watching are familiar with Nvidia, but for those who are not, Nvidia got its start really in the computer graphics space. So the idea being that, people wanted to, when people want to render computer graphics, or you say you want to play like Batman on your computer, or you want to render a molecular dynamics simulation, the idea of using traditional CPUs or sequential processors to do this is sort of it's an imperfect solution, in that when you have something like a problem where you want to render a bunch of pixels, if they can be rendered in parallel, you get a much greater efficiency, much greater, efficient use of power and of throughput and of latency. And so this is where Nvidia invented really the GPU, the graphics processing unit, to be tailored to this type of problem where you have a bunch of pixels. So maybe you want to render, the top left pixel in a computer graphics application, and you have a 1,000-line computer program that needs to run to compute the results. So if you're using a graphics processing unit, GPU, you can render those results, maybe this pixel and all of the rest of the pixels in your image in parallel, similar to maybe the molecular interactions in a molecular dynamics simulation. And so GPUs are really this massively parallel architecture that can accelerate these fundamentally parallel workloads. And so over time, people figured out that not only for computer graphics and for simulation or visual tasks, but for more general math computing, so things like linear algebra, they're also really well suited to a parallel computing architecture. And so in the early days of figuring this out, people initially tried to sort of trick the GPUs to accelerate their math by making their math application look like a graphics application. And so in the early days, this worked really well, and this helped people gain some speed ups. but the caveat here being that you had to really understand the fundamentals of how things like shaders and visually specific GPU computing paradigm design concepts worked. And so over time, Nvidia created these more high-level software libraries, things like CUDA, that would allow people to define a more general piece of high-level code and then have it be compiled down into something the GPU can understand and accelerate. And then starting in the early 2010s, we started to see this sort of organic development of the advent of a lot of artificial intelligence research, whereby people figured out, they want to run these big, large, deep, composable hierarchical neural networks. And they think that if they sort of scale them up to a really large size in terms of number of neurons and size of labeled training examples in a supervised context, they can get some really good results. They can get some sort of state-of-the-art performance. And really the only way that they were able to do this with sort of the amount of complexity in the network that they believe they need and the amount of labeled training examples is to use something like GPUs to accelerate that work. And so today, we do still very much care about computer graphics, but it would be more apt to think about Nvidia in this context as an AI data center company. Another way to think about this rise of GPU computing is in the context of Moore's law. And so for a long time, the progression of computing, which was depicted by single-threaded performance with CPUs and sequential processors, Moore's law would predict that basically every year you would get about 1.5 times faster, and this would be because the size of transistors would shrink, and you would squeeze more sequential optimization out of that instruction set. But really, starting in the 2010s, we're seeing Moore's law plateau, where you can only make transistors so small before you run into things like submicron effects. And really, we no longer see this predictable 1.5x performance improvement per year. And so when people want to continue to go faster using CPUs for that purpose, it's really no longer giving you this predictable benefit. So this is where GPU computing becomes really valuable, in that you think about these problems no longer as a single-threaded problem, but as a multi-threaded or fundamentally parallel problem. And now with GPU computing, we can get back on this path of having predictably large increases in computing performance year over year. And as I mentioned, really the core contribution to how this is possible and is very easily possible for most practitioners is through this software library called CUDA, and that stands for Compute Unified Device Architecture. Anyone who's using GPUs today is probably familiar with that. They have to go and download the CUDA toolkit and CUDA driver to actually be able to use the GPUs on the system. Basically, this is just an interface, you can think of it, for taking a high-level application or algorithm, defining it in some high-level programming language, maybe it's Python or C or C++, and having a compiler which can compile it down into binary instructions that the GPU can then go and implement and accelerate. And so today, NVIDIA, as I mentioned, many people think about NVIDIA in different ways. The real most useful way to think about us is as a platform company. And this is a high-level overview of a wide part of our platform, although it certainly doesn't encompass everything. And so if we think about it, starting from the bottom, the fundamental lowest level of this platform is the GPU. And so we just introduced a new GPU computing architecture, Ampere. And when we have GPU computing architectures, there's several ways in which somebody can interact with them. You can buy, a Tesla GPU, which is a sort of enterprise class GPU individually. You can get access to a virtualized GPU. We build our own high density data supercomputers meant for the data center, and we have partners and OEMs that build their own flavors of those as well. And we're also available in every major cloud service provider. So the one thing that keeps all of these different types of GPUs having a consistent software experience is that they all are going to use the same CUDA library. And on top of this CUDA library, you're going to get what we call CUDA-X or CUDA accelerated libraries. And so these are going to be collections of primitive operations that are going to be important for certain types of use cases that are going to be all collected together and available through an NVIDIA SDK or library. So for example, in the high performance computing space, we could be talking about things like QBlast for linear algebra, or QFFT for fast Fourier transforms. More generally, in the AI space, we could be talking about cuDNN for deep neural networks, or something like Nickel for collective communications to help us distribute our work among many GPUs or many nodes. There are these other libraries which are going to be the central message of this talk, called QDF, QML, and QGraph, that I will get to, which is basically going to be fundamentally important libraries for things like data frame manipulation and machine learning and graph analytics. But really, for a practitioner, you shouldn't care too much about any of this low-level stuff. You really just want to be able to use a high-level application or framework and let it accelerate your code. So in the HPC space, maybe this is molecular dynamics, and you want to use something like NAMD. You just want to be able to define your problem and have the GPU accelerate all the work without you knowing too much about what Ampere is, or CUDA, or QBlast. On the deep learning side, I'm sure most of you are familiar with popular libraries like TensorFlow or PyTorch. Basically, it's super easy today to get started with one of these libraries and just define your neural network, define your graph, and then say, basically with a single flag, I want to run this on CPU, I want to run this on GPU, and all of the hard work, all of the heavy lifting and plumbing to actually get that code not only compatible with the GPU, but running really efficiently on a GPU, is all sort of done behind the scenes, away from view. And this makes this a really powerful experience, in that you can have practitioners who know nothing about GPUs, who just simply know a lot about, for example, deep learning, and they have access to all of this GPU computing and parallel computing power. So lastly, on the machine learning side, which is largely dominated by things like scientific Python, we have this ecosystem we call RAPIDS, which is the central message of the talk today, which you can think of as trying to replicate the success that's been had in the deep learning space for something like more generic machine learning workloads. And so I'll take one quick pause to talk about deep learning, to sort of get some inspiration for how RAPIDS is going to work and is going to be useful for people doing machine learning today. If you look at the deep learning space, and as I mentioned, TensorFlow and PyTorch, you go and you can look at the documentation, and you can install the framework and play around with it yourself. You'll notice that the semantics of CUDA are implicitly built into the framework themselves. So the ability for the framework to understand what a CUDA device or a GPU is, and to actually be able to run your graph sort of transparently on those devices, is all built into the construction of the framework itself. It's very easy to, in the TensorFlow context, define I want to run on a CPU device, or I want to run on a GPU device. And in the PyTorch context, you're running on a torch.device where you pass in CUDA. This is going to be very simple, very straightforward for somebody to take their work and to run it on a CPU or GPU transparently. And all of the nuance and intricacies of doing things like sophisticated multi-GPU parallelism or model parallelism is all going to be a high-level primitive operation in TensorFlow or PyTorch. And this is a big reason why GPUs and deep learning has been so synonymous with each other. Another way to think about how this relationship is really important is just observing the trends that are happening specifically in the deep learning space, but more generally in the AI space. So you can think about how much data is being generated. You can sort of get an idea of this in terms of the number of zettabytes that are generated every year. And then if you look at how much AI research is happening, so the papers that are submitted to high-profile conferences such as NeurIPS and CVPR, you get a sense that there's a lot of interest and a lot of activity in the space. And then if you look at this graph that was a joint collaboration between OpenAI and Nvidia, you'll see that for each green dot here, this is a representation of a state-of-the-art model. So in 2012, we're talking about a model like AlexNet, and in around 2015, you had ResNet. Around 2018, we're talking about things like WaveNet and BERT. And when you look at when you measure, I should say, the complexity of these networks, one way to do it is to look at, okay, so if I had access to a petaflop of performance, so if I had the ability to run a quadrillion floating point operations every second, this is a measure of how many days it would take me to train that model. So if I had, for this thought experiment, a machine with 1 petaflop of performance, so it could produce a quadrillion floating point operations every second. To run AlexNet, it would take you about, a hundredth of a day. So it'd take on the order of minutes. For something more complicated like BERT, it might take you something like 10 days to train. Basically, the observation and the point I'm trying to deliver here is that over time, models are getting more and more complicated. And if you are interested in training and experimenting with things that are considered state-of-the-art, it now becomes completely necessary to think about GPUs, to think about massively parallel acceleration, in that it becomes very difficult to train for example, GPT-2 model on CPUs in the way that you'll have access to much less than 1 petaflop of performance. And I should mention, just out of interest here, that for the last couple of years, Nvidia has been producing very high density supercomputers that actually have 1 petaflop of performance or greater, such that when AlexNet was first introduced and these machines didn't exist, it took on the order of a week or so to train the AlexNet model, whereas now today we can train these things on the order of minutes. And so really what I'm trying to get to here is that doing really good state-of-the-art deep learning research and more general AI research, it's becoming more and more important to have a good understanding of parallel acceleration and GPUs and distributed computing in the way that you can sufficiently train a large, complicated model in a reasonable amount of time.
Griffin, I think it's good to have one clarification question. I always had this question. Maybe some people don't know, but like, can you explain the petaflop in 1 or 2 sentences if it doesn't take so long?
For sure, yeah. So a flop stands for a floating point operation, and flops would be a measure of floating point operations per second. So one way to think about this is, if you're defining something like a neural network, it's going to be composed of a bunch of operations such as multiplications and accumulations. So each multiplication would basically be sort of using the default behavior of something like TensorFlow or PyTorch, right? It would be taking a 32-bit floating point number and multiplying it with another 32-bit floating point number. And so a flop is basically a description of exactly that, is a floating point operation. And a petaflop or petaflops, so is basically a peta amount of floating point operations every second. So 1 petaflop would be doing a quadrillion multiplications, for example, in 32-bit floating point every second. And so flop is a really good way for us to measure the amount of complexity or the amount of computations that are necessary to train something like a state-of-the-art deep learning model. And so you'll see that term flop floating around a lot, no pun intended, in the way that we describe the capacity of deep learning hardware.
Awesome, thanks.
No problem. So I took only a quick deviation from the main thesis of this talk to talk about deep learning, and now really what I want to get to is the meat of this conversation, which is about machine learning, so more general machine learning work. And so if we think about the inspiration that we just talked about from deep learning, what we would need to see in the space of machine learning to have it be as ubiquitous of a behavior of the interaction between practitioners and GPUs is we would need to see, for all of the important scientific Python libraries that people care about, we would need to see them inherently support GPUs in order for this to be successful. And that's a very difficult problem to tackle, because in deep learning you have a more, I want to be careful about my language here, but basically you have a more constrained set of things that people are experimenting with. Like, when you know that you're going to be using a neural network, you can make some general assumptions about the behavior of that network, and you can really use things like cuDNN, right, deep neural network primitives like 2-dimensional convolutions or just simple dense matrix multiplications to accelerate that code. In machine learning, when the space of possible models and iterations of those models that people are concerned with grows, it becomes a bit more difficult to have GPU support for all of those different things. And so Rapids is a very large effort, and it's a very involved undertaking. And one way to think about it, though, is that for all of the popular, important libraries and tools that people are using in the machine learning space, so for example, pandas for data frame manipulation, or scikit-learn for machine learning, Rapids is a way to develop GPU accelerated versions of that code. So for example, with pandas, we have a library called QGraph, which is meant to be a sort of API replacement for pandas that'll work in very much the same way that pandas does. And similarly for scikit-learn, we have QML that would be, again, a very familiar Python API that would be a drop-in replacement. And so that's going to be what I'm going to be talking about today, which is the Rapids platform. And so I'm borrowing some slides from Josh Patterson, our senior director on the Rapids engineering team, which is I'm going to borrow a subset of his slides that he releases on every minor revision to Rapids, and our latest being release 0.14, talking about sort of the new improvements to all of the different tools and libraries that are a part of the Rapids open source ecosystem. I'm going to be talking through a few that I think are important to be aware of, and then pointing everyone to where to learn more and read more about all of the things that encompass what Rapids is today. So a good way to think about Rapids is if you look at the open source data science ecosystem today, there's a bunch of stuff in it, right? If we think about the main components being data preparation and then model training and visualization, we have a bunch of really popular libraries and tools that have sort of floated to the top of what people find to be, the most usable and powerful and dynamic. So things like pandas for analytics and scikit-learn for machine learning, NetworkX for graph analytics, for deep learning, PyTorch, TensorFlow, MXNet, and others, for visualization, things like Matplotlib. So you can think of Rapids as taking all of those individual components and having a GPU accelerated version of it. So as I mentioned, QDF and QML, QGraph for graph analytics, and QXFilter and PyViz for visualization. So a bunch of stuff that takes what people are already doing and having a GPU accelerated version of that. Maybe a more general way to think about this is how Rapids fits in the evolution of data processing. So if we think of the beginning of this processing evolution as the Hadoop paradigm, where you can create the thought experiment where you have a pipeline that has three general phases, as I mentioned. So you're doing a querying operation, ETL operation, then a machine learning training operation. In the Hadoop context, you would do each of these operations in your pipeline, and between each, you would have to do a read and a write from the Hadoop file system to share the data between each stage. And this is where, as we move down this chart, that Spark had a really important contribution, which was this idea of in-memory processing, where, yes, we're going to be doing the same query and ETL and machine learning training operations, but by using a Spark in-memory data format, we can save on the expensive read-write operations that are the intermediate sort of necessary functions between each of these steps. And by saving in the intermediate overhead, the entire pipeline gets something, between 25 and 100x improvement in speed up, while using less code and having a flexible language. So moving further down this idea of moving into this GPU paradigm of using traditional GPU processing, by using GPU processing in place for your query or ETL or your machine learning training, everything gets much, much faster. However, in the traditional context, you would still have to be doing reads and writes to pass that data between the CPU and GPU for each step of your operation. And so it's a good but an imperfect solution, whereby Rapids introduces this idea of not only shrinking the time for each of your operations by accelerating them on GPU, but also removing the intermediate CPU and GPU read-write transactions, which overall save you an incredible amount of time, somewhere between 50 and 100x improvement, depending on the particulars of your problem. But this is really the core contribution of Rapids, is by using something like Apache Arrow as an in-memory data format and using GPU accelerated math, we can shrink the total time to insight across an entire pipeline by a significant amount. So I'm going to touch very, very briefly on a few of the important libraries that I think that a lot of people would be better off knowing more about. So the first I'm going to talk about is QDF, which is the GPU Accelerated Data Frame Library. So we estimate through our research that the average data scientist spends about 90% of their time in ETL. And this is in opposition to actually doing something more interesting, like training a model. So if you look at a CPU-powered workflow, you can imagine somebody configuring an ETL workflow in the morning, and then starting that ETL workflow, but then getting a cup of coffee, waiting for it to finish, maybe recognizing they made a mistake and having to restart it again. Maybe they're drinking too much caffeine, they switch to decaf, and then maybe they find some error in the ETL operation, so they have to restart it again. And all of a sudden, that simple ETL process consumed their entire day. Whereas if you look at a GPU-powered workflow, the vision here is really to have something where people can configure their ETL workflow in a way that they're accustomed to, but by enabling this on GPUs, the time to run it gets shrunk significantly, so that if you make mistakes or you forget to add something, or there's an error in the result, the opportunity cost of how long it took to figure that out is much smaller, and people can get to things like training their model and validating their model and testing it much more quickly. And all of a sudden, the same researcher who has sort of access to a similar amount of sort of experimental opportunity is now going to be much, much more productive. So the heart of the ETL component of Rapids is really this library QDF, which is as I mentioned, the data frame library. So this is going to be, as I mentioned, a Python library for manipulating GPU data frames, and it's going to follow the pandas API. So if you do something like pandas.readcsv, now it's simply going to be QDF.readcsv, and everything else is going to behave the same. It's just going to happen much, much faster. So really, QDF is an interface to a CUDA C++ library, but practitioners don't have to know or think about that, right? They're just going to interact with QDF as if it were pandas. And so you can create GPU data frames in QDF from things like NumPy arrays or pandas data frames or PyArrow tables. And it also supports JIT compilation of user-defined functions using something like Numba. You can get a feel for the syntax on the right side of this slide here. So you can see this pipeline where somebody's doing a QDF.readcsv, so they have a CSV data set that they're trying to read in. And with QDF, it's going to happen much, much faster. And then just say they want to convert it to a pandas data frame because they want to do something like get access to a pretty printing function. Well, that's as simple as just taking that GPU data frame and saying, .to_pandas, and that's going to convert it to a pandas data frame because it's very interoperable. And then from there, you're just going to behave like you would be in pandas. So if you want to extract some, in this example, the first character in the entry, and then get rid of the plus sign and convert to an int, you're going to use the same syntax you would be using as if it were a pandas data frame. And if you want to do anything like a string replace or whatnot, it's all going to feel very familiar to you if you've been using pandas in the past. The main difference here, and that I'm going to substantiate with this slide, is that it's going to be much, much faster. So taking a look at a quick experiment where we look at comparing QDF versus pandas. So in this experiment, we're running on for the GPU, we're running on an Nvidia Tesla V100 with 32 gigs of HBM memory or high bandwidth memory. And we're comparing to an Intel Xeon CPU and E5. And the experimental setup here is that we're taking these int32 data frames and int32 value columns, and we're doing a bunch of operations such as merge, sort, group by, calculated for each value column. And so if we have if you can see the colors, the purple columns or the purple bars would be examples of this for 10 million rows, where the light blue columns would be for 100 million rows. We can see that for a merge operation, it's going to be, for example, 970 times faster to run it on QDF on a GPU versus pandas on a CPU. So this would be the difference between having something take 970 seconds on CPU versus 1 second on GPU. And so we see similar behaviors for doing a sort or a group by, where we get some amount of hundreds of times of performance improvement. And for this and for the rest of the benchmarks that I share, it's important to keep in mind that mileage will vary depending on the density of the math and of the data frames that you're doing, on the particulars of the operation and how much it can be parallelized, and of course on the particular hardware you're running on. But really the spirit of this is, whether it's 1000x or whether it's 100x or whether it's something in between, really there's a huge incentive as your amount of work grows and as your pipeline becomes more sophisticated to want to use something like a GPU to reduce the time to insight for each stage of that pipeline. So moving over into QML, which I think would be another interesting library for a lot of people. This is, again, machine learning, and in the spirit of scikit-learn, this is a library that's a Python match for the scikit-learn API, but again, this is going to be using GPUs to be accelerated. So here's a quick example of a make moons piece of code. So on the left, we're using sklearn datasets, and then we're importing make moons, and we're just drawing it out. We're just calculating the moons, and then we're drawing it out using pandas data frames. So if you wanted to do this on GPU, instead of an import pandas and a pandas.data frame, you replace that with an import QDF and a QDF.data frame. And as long as you installed QDF properly and you have a GPU on your system, everything is going to happen the same from a result perspective, but much faster from a practical point of view. And then on the right, we have a little DBScan example. So instead of doing from sklearn.cluster import DBScan, you would just do from QML import DBScan, and then everything else would work the same. It would be a bit difficult to sort of go over all of what exists in QML today and what we're working on in the future. So I would encourage anyone who is not familiar with this to go and take a look at our QML project, what exists and what's on the roadmap. And if there's anything that doesn't exist that somebody feels strongly about it should exist, please give us feedback and open a feature request or simply just get involved in some of the chat activity and let us know what you'd like to see. But similarly to the behavior we saw in QDF, a similar experiment of comparing a V100 to a dual 20-core CPU when we have really large data frames. So in the purple bars being 4 million rows, doing PCA or doing linear regression or ridge regression, we're seeing speed ups anywhere from on the order of 5.9x speed up on ElasticNet to 120x speed up on PCA for 2 million rows, and then here was 4 million rows for 5.9. You can see that obviously, again, mileage will vary depending on the particulars of the operation and of the size of the data set. You can get a general idea, though, that as you increase the size of your data, right? So if you have more millions of rows, the speed up tends to be greater. And you can get a feel for the fact that GPUs like to be consumed with data, right? So if you're underutilizing a GPU, you're only throwing a few thousand examples at it, only maybe using 1 gig of the 32 gigabytes of memory, there's going to be a lot of wasted space there, and so it's not going to perform as efficiently as possible. The GPU shines when you give it a lot of data and you consume all of its resources, where it can sort of maximize the amount of throughput and the amount of data that it can process every second. And similarly on the right, for a few other examples for things like UMAP and DBScan, we're seeing somewhere between 10x, 3.x here at the low case for a KNN on 16K rows, but anywhere as much as 730 times faster for SVC RBF for 64K rows. Another thing that would be important to be aware of, if anyone is not, is that we recently announced that Spark 3.0 is going to be GPU accelerated. And I know I've probably made it seem like the only thing that we're doing here is accelerating these scientific Python libraries. But really, a lot of people are simply going to be using Spark now and in the future. and having more awareness of GPUs as a consumable resource in Spark 3.0 is something that we've thought a lot about and we've put a lot of effort into supporting. And so hopefully the vision here in the future is that people can continue to use Spark as they always have, but a lot of the goodness of Rapids that's been created and talked about in the previous few slides and everything that I haven't mentioned so far is going to be used under the hood, similar to the deep learning examples I gave before, sort of away from sight, so that somebody can just be interacting with Spark as they always would. But if they're doing something that can be parallelized and they're using a sort of Spark 3.0 and they have a GPU, everything is going to happen a lot faster. So finally, the last bit I'm going to talk about is QGraph for graph analytics. So this is, again, it's going to be a graph analytics Python library similar to NetworkX. That's what the API will look like. So the focus here on features and user experience, is from a performance perspective, really the goal is to support a lot of edges, right? So up to 500 million edges on a single 32 gigabyte GPU. In addition to having multi-GPU support for scaling into billions of edges. We want to have seamless integration with QDMF and QML. So there's property graph support via data frames, so you can move from QDF or QML operation right into QGraph very seamlessly. And I don't think I made that point maybe clearly enough before, but a big contribution and design choice for Rapids is to take all of these individual component libraries and make them very interoperable, such that you can take a QML or a QDF operation and pass it into, maybe it's a deep learning framework, or maybe it's a visualization tool, or maybe it's something like QGraph. And so by having this ecosystem that has an interface that is respected among all these individual components, we can minimize the times at which we have to make those expensive CPU to GPU memory transactions. And to continue on the QGraph description, this is, as I mentioned, it's a Python library, so it's going to be very familiar if you're using the NetworkX API. And the growing functionality is that we have an extensive collection of obviously algorithms and primitive and utility functions, of which I try to summarize a bit on this slide here. Everything from spectral clustering to triangle counting to page rank to Jacquard and weighted Jacquard. There's a lot that exists today in QGraph that I think would be useful for a lot of people doing graph analytics. And again, if there's something that doesn't exist that you feel like should, please feel to reach out to the team and put in a feature request, and we can prioritize it as more requests come in. And again, not to bore you to death with benchmarking numbers, but looking at a bunch of different graph analytics data sets, you can see that as the data set becomes larger, the speed up, sort of moving from left to right across the graph, tends to grow as well. And for things like Louvain and PageRank and breadth first search and single source shortest path, we get anywhere from couple hundred times speed up to 6,700 times speed up, depending again on the density of your math and the particulars of the algorithm that you're working with. The spirit here, once again, is that this is just going to work much, much, much faster on GPUs, especially given that for graph analytics, a lot of the operations are fundamentally parallelizable anyway. So I know I've touched on a lot in this talk so far, and I didn't mean this as an exhaustive exploration of all of what exists in Rapids today. So if there's anything to take away from this talk, if this is a sort of too long, didn't listen summary, I would say that Rapids is very easy. So it's open source, it has familiar Python APIs. You just need a GPU to get started. It's also very easy to install. So if you look at the RAPIDS.ai page and you look at the way that you can install it through Conda or Docker or whatever, we have a nice little release selector you can use. The other thing I wanted to advertise very quickly here, and I'll just click on this link, and if it opens, I will drag it into my screen, is that if you go to the rapids.ai page and you look at get started, there's actually a button to launch in Google Colab. And so this is great in that if you don't already have a GPU right now in your environment and you still want to experiment and figure out how to use this and how it may affect your work, you can actually just spin up a Colab instance, which is already going to have a GPU for you, and using Nvidia SMI to get a quick command line understanding of what GPU you got. In this case, it's a Tesla T4, which is compatible with Rapids, which is great. You might not always get a T4 if you get something like a K80, which is an older GPU, which won't be compatible with the Rapids libraries. You can basically just restart your runtime, and if you get something like a P100 or a T4, it should be compatible with Rapids. And then we have a script to go ahead and install Rapids, something that lives on our RAPIDS.ai GitHub. It's basically going to pull down all the appropriate libraries and directories and build them all in this environment. And then you can go through and play around with QDF and doing something like a read CSV from QDF, taking a look at the speed up. You could compare it with a CPU operation maybe for your data set and see what the actual benefit would be for you. And then you can go and do something in QML, kind of get a feel for the behavior and the interaction. Hopefully, if you're already using these libraries, it should be very familiar. If you haven't been already using them and you're curious, there's a lot to go read about, and we point to some nice next steps. So we actually have a bunch of notebooks compiled on the rapids.ai GitHub where you can go and actually do full sort of pipeline experiments and walk through a bunch of more sophisticated examples to really show off the justification for wanting to use something like a GPU accelerated library. So finally, I mentioned Rapids is easy. Rapids is also fast. As you saw, the pipeline speed up can improve from hours to seconds, depending on the density of the math and the particular algorithm you're using. I didn't talk a lot about Dask today, but basically we scale very seamlessly with Dask to scale up to larger models and larger data sizes. Another thing I didn't really get a chance in our short time today to talk about is that Rapids is very integrated with the cloud. So we work closely with major cloud providers, and we have lots of code samples to get people started, whether they're using Google or Amazon or something else. There's a link here to a hyperparameter optimization page, which I think is really useful if that's something that you've been doing in the cloud, if you've been doing hyperparameter optimization and you're curious about how much faster it could get with GPUs. And really to extend that idea further, Rapids is very cost effective in the way that if you're doing, in this use case example, a 100-job random forest hyperparameter optimization for an airline model, yes, a GPU node in the cloud would be more expensive initially, but given that it can be many, many times, in some cases orders of magnitude faster, your total cost of running that hyperparameter optimization job is going to be much, much lower using a Rapids paradigm as opposed to a scikit-learn and a CPU paradigm. And so the last thing I'll leave everyone with, and because what I really want out of this talk is for people to have an understanding of how they can get started with this work and where to go when they have questions. So the most obvious question is, where do I get the software? So you can go check it out on GitHub. You can install it through Anaconda. We have a Docker repository we call NGC, the NVIDIA GPU Cloud. You can grab it from. Similarly, we have access or we have these containers released on Docker Hub as well, if that's your preference. Please join the conversation if you have some insight or some ideas that you think are useful. We have Google groups, we have Docker Hub, we have Slack channel and Stack Overflow, where we're very active in continuing the conversation about GPU accelerated data science. And then finally, please contribute back if you can, whether it's just identifying an issue or a feature request or a pull request, or whether you think you have an interesting blog or tutorial where you can teach other people on how to do something really useful with Rapids. This is really the way at which we can all help each other, is by learning the tools better, learning the limitations of the tools, how we can improve those, and then coaching other people and educating other people on how they can use them to solve their problems. So I'll leave you with both the email of myself and Mukundhan. As I mentioned, we're part of a large team of people at NVIDIA who care about helping our customers. And so there's a lot of different channels to get your questions answered, and sometimes it's hard to figure out exactly where you should be placing your question. So if it's at all unclear, please feel free to start with us, and we can point you in the right direction. So that's the end of my talk. Thank you so much. I'll turn it over to Ali to open it up to questions.
Awesome. Thank you, Griffin. So I just want to mention that if you go to our website, ai.science, and go to this events page, you would be able to find the PDF version of the presentation. So you can go to the references and URLs Griffin and Mukundhan actually put in. And please feel free, if there is any question, post it in the chat. I actually noted some questions here, like a couple of questions. So in Spark 3, you mentioned that so you can actually use it like a GPU accelerated operation, the exact same way as the older versions of Spark. Does it mean like with the minimum effort and minor changes, you can actually use the legacy code and leverage the GPU acceleration?
So that's a really good question, and I don't know if I can adequately answer it in the way that you would probably want to see specific examples of what the code syntax looks like to get a feel for what the effort would be. But really, yes, the spirit of Spark 3.0 is to have you be doing very Spark-esque commands, right? So not really thinking about GPUs, only that, similar to all of the other examples I've given, if it's something that can be parallelized, if it's something that can be accelerated on GPU, all of that work should be done for you in the way that you shouldn't really have to think about it. And really the best way to get a feel for what that environment looks like is that there's a Spark ebook that you can Google from Nvidia on Spark 3.0 that gives a really exhaustive breakdown of all of the design choices that are made here and what that'll look like for the practitioner. But to give a quick summary of my feeling towards the question is, yes, it's going to be very transparent. The particulars of each specific operation that somebody may ask about might vary, but in general, yes, you're going to be doing very natural Spark stuff, and if it can be accelerated on GPUs, it will be.
Awesome, thanks. Maybe I can find a Spark book and just paste it in the chat for everyone to have access to. Another question, which is particularly my own question, like the real world examples and projects I usually deal with at work. So basically, some of the projects, they deal with a lot of like large data sources, like that makes sense to definitely use a GPU accelerated solution, right? Like RAPIDS or Spark 3. But some of the projects aren't necessarily that like in terms of the amount of data, they aren't that big, and I don't really have like any performance issue with using GPU instead. But the question is, what is that point? Like how much data is big enough to consider using GPUs instead? And also, like, I don't know, maybe the answer is like, regardless of the size of data, it's better to use GPUs. Do you think, like, even if I have a few gigabytes of data, that's already better to use GPU instead?
That's a really excellent question. And it's hard to identify what the specific inflection point would be so that you could have a rule of thumb that says, if I'm bigger than this in terms of size of the model or size of the data, then GPUs are suddenly worthwhile to me. It's almost like if you wanted to drive, right? Whether you're driving yourself in a car or in you're moving, and whether you do a bunch of trips from your old house to your new house in your car, or whether you take one big moving truck and fill it up. If you're just going down the street, maybe it makes sense to take your individual car. It's a little bit quicker. But if you're moving across the country, it makes sense to have higher throughput and to load it up. And the overhead of of actually like getting the truck loaded and started and moving is very small in relation to the overall trip when you're moving across the country. I would say that for GPUs, if you're just doing very small experiments, you have maybe hundreds of examples and you're using fractions of a gigabyte of memory to do so, then the GPU doesn't become as attractive, because there's a certain amount of overhead just to use the GPU in general. And an example of that is the time it takes to copy data from the CPU to the GPU. But as soon as you have, and I'm going to be very hand-wavy about this because, as I mentioned, it's hard to identify the exact inflection point. But once you get into, as you mentioned, gigabytes of data, where you have thousands or hundreds of thousands of examples, whether your model becomes to have similarly like hundreds of thousands of parameters, of operations, of flops, as we've talked about, then quickly it becomes very efficient to use the GPU. So I would say a good rule of thumb, and maybe there is no good rule of thumb, but in general, yes, if you're using gigabytes of data and of storage to store your model parameters and activations and whatnot, then a GPU does make sense. And that's usually for a fully fledged experiment, even if it's a one big large model or a small model that you run in a hyperparameter optimization paradigm many times over. If you're doing something much smaller than that, it may not be as necessary to use GPUs, because GPUs really shine and are most effective when they're being fully utilized. And for like a V100, as we mentioned, that's 32 gigs of GPU memory. The T4 that we shown that I showed in the example on Colab is 16 gigs of memory. So really, once you get into that size of experiment, then of course the GPUs are going to make sense. Anything much smaller, maybe it's just a little prototyping experiment you're doing to get the syntax right, then a CPU is probably fine.
I see, great. So there is one more question, and it's related to QGraph. And I think this is a really great question, because lately we have seen a lot of great researches came out around like graph analysis algorithms, and which we had them presented in our channel. So what is the best source of learning for QGraph?
Yeah, that's a really good question. So for learning QGraph, of course, as I mentioned, it's really useful to go and get yourself familiar with the code itself. So there's going to be the QGraph GitHub and the documentation that's available through RAPIDS.ai. That's a great place to get started. But one of the best sources of knowledge that I find, even personally, is that we have these big conferences every year called GTC, which stands for GPU Technology Conference. And it was virtual this year for obvious reasons. We host our main one out of San Jose in March. And so if you look up GTC digital content, you can actually find a bunch of really awesome QGraph, for example, and there's many Rapids and QML and QDF and whatnot. There's sessions, so there'll basically be a speaker and a presentation that's talking through. In some cases, it's general information about something like QGraph, and in other cases, it's a real world example, like this company used QGraph to solve this problem, and this is exactly how they did it. And those are really good sessions to hear, sometimes directly from the developers of QGraph themselves, or from customers who are very familiar with QGraph and have some really good insight in how to effectively use it. I think those are the types of sessions that are really valuable if you're going to choose an hour of your time to spend learning about QGraph. Sometimes the best thing to do is to actually look up a GTC presentation on the topic. So that would be a great place to start.
Perfect. Thanks. There is one more question came up, and it might not be that easy to answer, but someone said if we were to run the NVIDIA code locally, what laptop would you recommend?
Yeah, that's a really hard question to answer. To give everyone's hardware requirements are gonna be different. I would say in general there are, yes, many laptops with dedicated Nvidia GPUs for which doing small scale experiments like this is very possible, and you can have a good amount of success and a pleasant user experience in terms of the amount of time it takes to run the code. I would say though, in general, most people are moving away from developing and running things locally on laptops and are moving towards actually using their laptops just as a way to access remote resources. So whether that's something you can get in your grad school lab, or something you can get at your company, or even, as we mentioned, just looking in Google Colab and getting access to a GPU there. I feel like for most people, unless it's a very small experiment that they're able to get a good environment on a GPU laptop, they're probably going to want to look into remote resources somehow. So whether that's cloud service provider, whether that's Colab, or whether that's localized infrastructure at your school or at your work, I think that would be an important thing to consider, is that the best user experience will probably be from having a GPU that is actually like a full data center ready GPU that's going to have much higher performance than a laptop GPU.
Gotcha. Awesome. Okay, I don't think there is any other question. I would like to thank you, Griffin and Mukundhan, and the Nvidia team in Canada for the great presentation. And to our audience, please feel free to check out our recent workshop. Today is the last day for the early bird discount, and it's all about like building ML products from concept to MVP in 5 weeks. And if you have something to mention, Griffin, at the last words, please feel free to mention. Otherwise, we can close the live streaming.
That's it. Thank you so much for organizing it, Ali. I'm glad we could do it.
Awesome. Thanks.